Hi everyone and welcome back to this series of electrical A6 power systems and machine questions. This is from May 2016. I have solved this question before, but one of my friends basically pointed out there's a mistake in the question, and as I progress in the question, I will mention what is the mistake. This is magnetic circuit question number 2. I solved a question before about magnetic circuit, which is when you have your mu as constant value. Okay, so this is one type of question. Here we have the BH, and mu, as you may know, is equal to B over H. And you can see here that as you divide B over H, it's changing, it's not constant. Okay, so that is the major difference between this type of question and the question number 1. And basically, these are the two main concepts if you talk about magnetic circuit. Either mu is constant or you have the BH curve. So we are giving this magnetic circuit here, and you are giving that the flux is 2 milliweber in the air gap. So the flux here is given to you as 2 milliweber. And you are giving the number of turns here as 500 turns. And basically you are asked what is the current that comes here. And you are given all dimensions about your circuit. So the first thing here you need to do is to start from where you know the flux. And you try to find the flux density B. The flux density B is basically equal to that flux divided by the cross-sectional area, which is equal to 2 times 10 to the minus 3 Weber. Convert everything to Weber, divided by the area here, and the area of the magnetic circuit is 25. You have to convert that to meter square, so times 10 to the minus 4, and you will get 0.8 Tesla. So this is your B. Once you know your B, this is 0.8 here, you can find from the curve your H. Now here you will not be able to find exact value, so you can say that your H is basically 150 ampere turn per meter, and from this your mu is equal to B 0.8 divided by 150, and this is equal to 0.0053. That is basically your mu. My mistake in the question, I assume this mu is the same in every single branch, which is wrong. This mu is only valid from this point to this point in that path. So that is the mistake I have done. Okay, now once we know mu, now we are ready to start finding the parameters of the magnetic circuit, and now we need to basically redraw this as an electric circuit. So the Ni is what we call, this is your MMF, magnetomotive force, which is similar to the EMF, electromotive force in electric circuit, or the battery. So here we have the battery. And then this, all of this path is one reluctance. So we'll have here one reluctance 1. This shunt element is another reluctance 2. And then this L3 and L4 is reluctance 3. And we have here an air gap, so we'll have another reluctance RG. And here we have the flux 3 that we know, which is the 2 milliweber. There is a flux here phi 2 and phi 1 that we don't know. So this is basically your circuit. Now, since I know mu, I can find reluctance 3, which is basically, as we know, that the reluctance is equal to L over mu times A. And we have everything. So reluctance 3 is the path through L3 and L4. So it's equal 26 plus 26, because L3 and L4 is 26, times 10 to the minus 2, meter divided by the mu that we just calculate, 0.0053 times the area, which is 25 times 10 to the minus 4. And this will give me 39,000 to 45.3. Then I can also find the air gap reluctance, which is equal to Lg over mu 0 only, because mu r is equal to 1, and mu is nothing but mu 0 times mu r times the Ag. So Lg, the air gap length, is equal to 25 times 10 to the minus 3 centimeter. So 25 times 10 to the minus 3 times 10 to the minus 2 to convert that to meter, divided by 4 pi times 10 to the minus 7 times the air gap. The air gap is basically 26 centimeters square. So 26 times 10 to the minus 4. The question is, why the air gap has a larger cross-section area than A3 and A4? And this comes because of something we call the fringing effect. So if I zoom this area here, and the flux going from in this direction, in the air gap, there will be some little bit of flux fringing. So this is why we make the air gap area, cross-section area, is more than the magnetic material. And this would be equal to 76,516.8. Now we found these two reluctances. We know the flux. So we can find the total MMF between point A and point B, which is like finding the voltage, which is basically the summation of the reluctances times the flux. So you call this is MMF3, which is equal to phi 3 times R3 plus RG. So we have everything here. So basically it's equal to the flux 2 times 10 to the minus 3 times R3, 39,000 to 45.3 plus the 76,516.8, and here we get 231.5 ampere turn per ampere turn. So this is your Ni, 231.5. Until here, that is basically, this is the same as the previous question. Until here, everything is correct. Now, this MMF is equal to MMF2 as well, which is the driving force here. Okay. Now, this is equal to Ni equal to H times L. Okay. So the Ni is of course there is no N here, but this is basically like the voltage, like the MMF. Okay, so it is better represented as H times L. So from this I can find H, and this is between this point and that point, which is MMF3, but because this branch is in parallel with this, so it's the same as that branch. So your H would equal to MMF2 divided by L2. We have everything. So this is 231.5 divided by L2, which is basically equal to, where is L2? 24 centimeters. So 24 times 10 to the minus 2. And here we will get your H is equal to 964.6 ampere turn per meter. Now you come here and you find B. So this is your H2. So you come here, you go all the way up, and then you will find your B2. Now again, will be an approximation. So we can say this is approximately 1.37, 1.36. All are okay values. Okay. So now once you know B, I can find phi 2, because it is B2 times A2, which is equal to 1.37 times A2, which is your A2 is given to you here, as 12 centimeters square. So 12 times 10 to the minus 4, and this will give me 1.644 milliweber. Now that was wrong in the previous question. So let me come back here. Let me redraw the circuit again so that we can follow what is going on. So this is reluctance 1, reluctance 2, reluctance 3, R gap, reluctance gap, here RG. Okay, so now we know that the flux here, flux 3 is equal to 2 milliweber. And from the previous part, we know that here it is equal to 1.644 milliweber. Now we can find phi 1. So your phi 1 is equal to phi 2 plus phi 3, just simple KCL. And this will give me 3.644 milliweber. Now, once we know this, we can find the flux density 1 in here, in this branch, in that branch. So your B1 is equal to 3.644 times 10 to the minus 3 divided by the area here, which is basically is equal to 40 centimeters square. So divide by 40 times 10 to the minus 4. And this is approximately is 0.9 Tesla. So 0.9, you come here. So it's still, you are in the nonlinear region a little bit. So you go down here. It's around 200. So basically your mu is equal to, or mu1 is equal to B1 over H1. So basically equal to 0.9 over 200. And this will give me 0.0045. From this, I can find reluctance 1, which is basically equal to L1, which we have it here, 40 centimeter, divided by mu1, which we have it here, times A1, which we also have it here. When you do all of this, you will get this is equal to 22,222.2. So this is your reluctance, number 1. So now I know the reluctance, I know phi 1, then I can apply KVL to this loop, for example, here. But this is your main MMF, which is equal to Ni, is equal to reluctance 1 phi 1 plus MMF 2 or MMF 3 because they are the same. Okay, so this is equal to 22,222.2 times phi 1, which is 3.644 times 10 to the minus 3. Okay, then plus MMF2, which is equal to 2031.5. This will give me 312.5 ampere turn. Then your current I is equal to 312.5 divided by 500, and this will give me a 0.62 amps. And this is the current. So the mistake that I have done, I assume that the mu is constant for all the branches, and you can see here the mu actually is not constant.